visible?
Yeah, it is visible.
Okay. So let me start. Thank you, Nikhil. Thank you, Sunita, everybody in CMInDS for this opportunity and starting the talk series on this topic of sentiment and emotion analysis. So maybe the title is a bit catchy, but this is how sentiment emotion analysis researchers begin their work. They have this ambition of imparting sentiment emotion on computers and also seeing that the computers become more empathetic in their interaction. And this is the dream they pursue. Now, that presentation is constructed out of work done by a large number of students working in sentiment and emotional analysis with me, both at IIT Bombay and at IIT Patna. Now, the roadmap is as follows. I'll introduce briefly natural language processing because this is a diverse group of faculty members, researchers from various disciplines. I will also give a brief background of sentiment and emotion analysis, and then go to 3 specific works on imparting sentiment, emotion, politeness onto computer. May I also ask everybody to mute your mic if you are not speaking? Okay. Now, there is this proverbial story of Tower of Babel. We often ask why there are so many languages, and there is this mythological story that human beings wanted to reach the heavens, and they started constructing a very tall tower to reach the heavens. Then the gods became afraid, and they created many languages, which created a kind of barrier between people, and so they could not communicate because of the language barrier, and therefore the project fell through. So this is a mythological story, but it underlines the importance of shared ideas and communication amongst people, which is important for the success of any large endeavor. Now, natural language processing is the art, science, and technique of making computers understand and generate language. Language has content which communicates with our head, but language also appeals to our heart. It has emotional content, and there is this increasing effort at making computers have more empathy, understand emotion, understand sentiment. So difference in language leads to communication barrier. Difference in emotion also leads to communication barrier. I have this favorite example to convey the importance of natural language processing as an area. This is a real example. I have suppressed the name of the company and the organization. So an insurance company, reputed large insurance company, engages a startup to deal with the large volume of customer complaints. Even the startup cannot cope with the volume of tasks, and this needs automation. And this automation involves natural language understanding, automatic speech recognition, and most importantly, sentiment analysis. This is a situation which is very pertinent to our topic of talk today. Now, empathy really reduces the communication barrier. So we created a chatbot. We have been working on emotion-aware chatbots for quite some time. And recently we worked on a multilingual chatbot. So if you look at the conversational history, somebody please help me, I'm having the worst luck with your customer service. The generic response from a chatbot is, how can we help? This a lot of chatbots can do, but we embellish the output from the chatbot with some amount of politeness. We add politeness phrases. So help has arrived. We are sorry to see that you are having trouble. How can we help? So this expression is more polite than this generic response, how can we help? The system is also multilingual. Things like पिछले हफ्ते ही घर आया था और मुझे फिर से अपने इंटरनेट से समस्या हो रही है. So the generic response is आपके इंटरनेट के साथ क्या हो रहा है, wants to know the specific details. And the polite response is ये अच्छा नहीं है, मैं मदद कर सकता हूँ, कृपया बताएं कि आपके इंटरनेट में क्या समस्या है. So these kind of responses make the customer more comfortable and also possibly increase confidence in the service. Now, natural language processing has been around since 1960s, and it is understood that the crux of the matter is really ambiguity processing. And ambiguity is at the heart of many interesting situations, including humor. The two examples I give here indicate lexical ambiguity. Suppose the question is, what is the difference between in-laws and outlaws? The answer is outlaws are wanted. Now, there is a play on the word wanted, and wanted has many meanings, and one of the meanings is wanted by police. Then if the question is why one should never date a tennis player, the answer is love means nothing to them. So now here there is play on the ambiguity of the word love and nothing. Love has a specific technical meaning in tennis. Now, these are examples of lexical ambiguity or word level ambiguity. More complex and serious kind of ambiguity comes from structural ambiguity. So here there is an interesting sentence which appeared in Times of India. Maharashtra reports increased COVID-19 cases. Maharashtra reports increased COVID-19 cases. There are 5 words here. The meaning intended is it is reported by Maharashtra government that COVID-19 cases have increased. Now, something interesting happens when we look upon increased as the main verb. Okay, the main verb of the sentence is reports, as indicated by the root and the arrow going into the main verb in the dependency structure. Now, if the main verb is looked upon as increased and the arrow from root goes to increased, then Maharashtra reports becomes a noun phrase, the subject of the verb increased, and the meaning becomes it is the Maharashtra reports that have increased COVID-19 cases. Okay, so these kind of interesting possibilities emerge, and these are not really fictitious. Okay, we do see this kind of funny situations occurring when the machine processes textual data. Now, probably the most complex kind of ambiguity is at the highest level of natural language processing. This is pragmatic ambiguity. Passenger says, "Thank you for sending me to Delhi and my luggage to Mumbai. Brilliant service." A chatbot says, thank you for the appreciation." Now look at the body language of the lady. The text is, "Wow, well done," but the body language is completely negative. So this kind of incongruity between two modes of expression is something very fundamental to a complex problem like sarcasm detection. We need to catch these kind of incongruities either in the text or in different modes of communication. Now, natural language processing is really a layered process starting from morphology, where the word is broken into its parts. We look at the morphemes and segments and also the features of the word. Quickly, for example, is an adverb. Then move from part-of-speech tagging, which gives grammatical categories like noun, verb, adjective, adverb, and so on. Go to forming short phrases, non-recursive phrases, which is chunking. Create the parse tree at the parsing level. This is also the syntax level. Obtain semantic roles and precise meaning of the words. This is word sense disambiguation and semantic role disambiguation. And finally, move to processing of large pieces of text, which involves the 3 C's of coherence, cohesion, and co-reference. So this is the highest level of processing on the text. And if we also do pragmatic processing, then this is really a very complex task. But the whole pyramid is built on foundational processing at the level of morphology, part-of-speech tagging, and so on. NLP is also a 3-dimensional problem where there is this language axis and the problem axis. NLP researchers, computational linguists are interested in designing algorithms for a particular problem for a particular language. Maybe we're interested in building Marathi part-of-speech tagger, and then the algorithms will be created for this problem. So now this layered architecture, layered processing of natural language processing resonates well with deep neural networks. Maybe that is the reason why deep neural networks are showing pretty reasonable success in dealing with natural language processing problems. So in deep neural networks, we have multiple layers taking information at the input layer and producing decisions at the output layer. Now, if we have a sentence like "no dogs, please," which is ambiguous depending on where the pause is, "no dogs, please" would mean dogs are welcome. "No dogs, please," that would mean dogs are not welcome. This kind of ambiguity can be processed from the contextual cues by complex processing going from layer to layer. And at every layer, some kind of feature extraction takes place, and this information is fed into the subsequent layers. So, then in this process, of course, the neural network is very data hungry, and key role is played by data distribution, and probability has proved to be a very useful instrument in this whole activity. In neural networks, we essentially do non-parametric estimation, where we don't know anything about the underlying distribution of the data. Neural networks do require data of high quality in large amount. Now, this is an example of what probability can do for us. So this was a very intriguing example personally for me when I started working on statistical machine translation. So here is an example of what is called parallel corpus. There are two English sentences, 3 rabbits and rabbits of Grenoble. The corresponding French sentences are Troyen lapin and lapin de Grenoble. So this is what is called the parallel corpus. And from there, we can create word alignment. And we should note that there is no additional information, no syntax, no semantics, no other information is given, just parallel sentences. So here we see that the word rabbits appears twice, and just this advantage of the count of rabbits being more than other words counts is seized by an algorithm based on expectation maximization. And that produces word alignment. We start with uniform probability. We have no knowledge of what Troya corresponds to. So 1/4 probability is given to 3 rabbits of Grenoble. All these English words are likely to correspond to Troya. But just because of this advantage of count, rabbit appearing twice, this expectation maximization algorithm runs, and gradually the probability of correspondence between lapin and rabbit becomes a winner. So the probability goes on increasing, and the probabilities of other cells in the same row begin to get depressed. So this is the basic word alignment algorithm on which the whole structure of statistical machine translation or data-driven machine translation, which is non-neural, rests. So the current framework, of course, is neural machine translation, where this input sentence is encoded, and the encoded representation passes through the decoder. Yes.
In the previous slide,
yeah,
the Grenoble was a very unambiguous, right? It is a common in both English and.
Right.
But why I see like Grenoble in this last row assigned 1/3 probability to half, and also Grenoble is also 1/3. Why this?
Right. So similarly, 3 also is appearing only once. And Grenoble is a proper noun, but the system doesn't know that this is a proper noun. System has no information other than only the parallel corpora. Okay, so maybe you are saying that as the expectation maximization iterates and as the computation progresses, the Grenoble to Grenoble mapping probability also should have been higher.
Yeah, it's exact match here, right?
Yes, yes. No, actually, it is this count advantage of rabbit which begins to assert itself. Okay, more than word appears more than once.
Okay. Thanks.
Yeah. So in neural machine translation, we have this encoder-decoder architecture many times along with attention, which is used for translation. Now, data plus classifier is proving to be more powerful than human decision making in many fields of AI and many other activities in our real life. However, we know that machine learning algorithms fall in a spectrum, starting from table lookup, going through rules, through statistical classical machine learning like SVM, to deep neural network. The robustness goes on increasing as we go from left to right in the spectrum, but the explainability goes on decreasing. Deep neural networks with millions of neurons and many parameters are really very inscrutable. We do not know what is going on inside the machine. Natural language processing has many areas which are very useful. Machine translation, many of us use Google Translate, information extraction, OpenIE, for example, information retrieval, all the search engines, question answering systems like Alexa, for example, multimodal access, sentiment and emotion analysis. All these are very useful areas of NLP, but all of them depend for their core techniques on rules, logic, search, and machine learning. Now, the NLP work has been going on in the institute, in our lab, Center for Indian Language Technology, in the CSE department since 2000. And recently in 2015, when I was in IIT Patna, I set up an AI NLP machine learning lab in IIT Patna also. Now, coming to sentiment analysis, here is a brief background. Sentiment analysis is defined as a 5-tuple, where the third entity is most important, SO. This is sentiment about an object O on a particular feature of O. The opinion is held by H at a particular time T. Now, this kind of fine-grained definition of sentiment analysis is important. Otherwise, there is confusion about who has what opinion in a particular situation. So I give an example here. This is a complex sentence. I love the songs in the movie, though only the cast was liked by my brother, who said the director was of the opinion that the storyline, which is from a novel by Shakespeare, will be lapped up by the public. It is a long sentence, grammatically correct and well-formed also, but there are many entities, many opinions, and many targets of the opinion. So that is extracted from the text through mainly dependency parsing. The entity here is the movie, and there are aspects like song, cast, storyline. The opinion holders are I, brother, director, public. We note that Shakespeare doesn't hold any opinion, and the time is present tense, past tense, and future tense. So these kind of triples are extracted. This is a very important step in knowledge extraction from text. So I love song, brother like cast, director like storyline, indirectly, and public lap up storyline. So this kind of information extraction from text is very fundamental, and it is important for downstream application. Sentiment analysis is also a multidimensional problem involving different languages. Sentiment is expressed very differently from culture to culture, from language to language. The problem uses many features like discourse features, syntactic features, bag of words. The sentiment is expressed by means of discrete polarities or ordinal values or subjectivity, like positive, negative, neutral. Then there are decision-making systems based on rules or unsupervised, supervised learning, now deep learning quite a lot. Makes use of many resources like dictionary, ontology, and so on. So it's a complex problem involving many different kinds of tools and resources. Now, these days, multimodality is becoming important for sentiment analysis mainly because the data is in short supply. To make accurate decisions on complex emotional landscape and also on complex sentiment situations, it becomes very difficult to make any decision, mainly because of paucity of data. And neural networks are, of course, very data hungry. So this scarcity of data can be partially ameliorated by making use of multimodal signals. So if we have gaze, aversion, frown, frustration, then there is this is a negative situation, and thumbs down indicates that. Whereas excitement, head nodding, smiling, these are positive sentiment signals, and we see a thumbs up. Now, emotion analysis and sentiment analysis differ from each other in one fundamental way. Sentiment analysis is a 3-class problem. There can be positive, negative, and neutral sentiments. Emotion analysis has finer levels like anger, disgust, happiness, and so on. Now, psychologists and cognitive scientists have done fundamental work on emotions, and we see that the basic emotions are happiness and sadness. Then Ekman's emotions are 6 in number: anger, disgust, fear, sadness, happiness, and surprise. This becomes his 6th-class classification problem. And then Plutchik's emotions are 8 in number. They extend the repository of emotions. And India has also contributed to this kind of work on emotions. The Navarasa theory is famous, which every dancer, actor knows about. So there are these 9 rasas of love, mirth, fury, compassion, etc. Now, Plutchik's emotion wheel has another interesting facet. The emotions in the inner circle are most intense emotions. Then the middle circles has little less intensity, and the outer circle emotions are much less intense compared to others. For example, terror is very intense, fear is moderately intense, and apprehension is less intense. So this is a property of the emotion wheel, which is very interesting and important computationally. Now, between the two petals, there is what is called combination emotion. For example, if you have trust and fear, then that gives rise to submission as an emotion. And therefore, trust and fear are elements from which the emotion of submission can be constructed. So the implication for that is that this kind of regularities and combinations can reduce the data requirement. Now, we have been working on sentiment and emotion analysis for many years, about 20 years now. This matrix here shows different techniques which we have used on multiple types of emotion and sentiment analysis problem. For example, if I take sarcasm, this work began in 2013. Starting with rule-based systems, we moved to classical machine learning techniques and then to deep learning techniques. And similarly, for a basic sentiment analysis, emoji identification, emoji suggestion, and cross and multilingual sentiment analysis in dialogues, which is something which I'll expand a little more as we go ahead. Now, we take the first piece of work, which is dialogue, act classification, and sentiment. Am I audible and is my screen visible? Dialogue, act classification, and sentiment.
Yeah, it's
okay. Okay, thank you. So this is a situation, a task which involves multitask learning. So dialogue act classification corresponds to the intent of the speaker and also the response of the listener. So each turn is primarily a question, a statement, or a request for action. These are the 3 broad categories for classifying every dialogue turn. Okay, and quite a lot of cognitive science-based, psychology-based work has been done since 1990s due to Jurafsky, Stolke, Verbry, and so on. And but the fact remains that each dialogue turn is fundamentally a question or a statement or a request for action. Now, there are these nonverbal features like change of tone, facial expressions. They are important for response generation. The correct response really depends not only on the content of the dialogue acts, but they also depend on the sentiment and emotion of the input. For example, if you take this phrase "ha ji ha" in Hindi, this can denote agreement if I say "ha ji ha," or it can be a sarcastic statement "ha ji ha," depending on the tone of the sentence. And then the response of the listener or the chatbot has to be very different. So in this work, we have contributed to the community in the following way. We have created a emotion-aware dialogue act dataset. We call it EmotiDA. And we have given a solution for multimodal, multitask emotion analysis and dialogue act classification using deep neural network. And what is important is that we have showed that the response generation becomes much more effective and natural and much more consistent with the situation if we exploit multimodality. That means text, speech, and video, all the 3 modalities. And if we are respectful of the multitask nature of the situation, that means both content and the emotional content have to be taken note of. There is a lot of prior work in dialogue act classification, again starting from 1990s. And dialogue act classification actually is a sequence leveling problem, which is so well known to machine learning researchers, NLP researchers, of course. And we see from 2016 deep neural network techniques being used quite heavily in this area. So dialogue act classification is a sequence labeling problem because of the following example. So A and B are engaged in a dialogue. This is a two-party dialogue or dyadic dialogue. So the first is, so do you go to college right now? It is a yes/no question. Are you started to say something but stopped? So the label for this is abandoned. Abandoned is also a label. B says yes, yeah, which is a yes answer. That is the categorization. It is my last year. That is the statement from the B. And B also has a laughter. So laughter is the emotion part, which in traditional dialogue act classification is not exploited. Okay. Then you are A, so you are senior now. This is a declarative question. So you can see the dialogue proceeds this way, and each turn has to be labeled as a kind, as is it a question, is it a statement, what kind of statement, and so on. And again, if it is a question, what kind of question? Is it yes, no, or WH? If it is a WH question, is it a factoid question, or why question, or how question? So we can see that there is a hierarchy which begins to become useful, begins to become important for dialogue act classification. Now, we created this data set and contributed it to the research community, which is extracted from the videos of by looking at YouTube, MOUD, IEMOCAP, and so on. These are videos which are labeled with emotion. Now we have given them manually dialogue act classification. So this data was already emotion labeled. We have given them dialogue act. That means, is it a yes no question? Is it a statement? Is it an opinion? And so on. So we took two data sets, IEMOCAP and MELD. So, and the tag sets consists of 12 frequently occurring tags chosen out of 42 dialogue acts. And they're greeting, apology, command, question, answer, agreement, non-opinion statement, opinion statement, acknowledgement, back channel, and others. So these 12 tags were chosen, with which we label the data. And the amount of the data is about 10,000 utterances from MELD and about 10,000 utterances from IEMOCAP. So 3 annotators graduate in English. They were appointed to do this annotation on the data. And inter-annotator score or agreement was more than 80%. We had to do a little bit of mapping from one data set to the other. For example, joy tag of MELD was mapped to happy tag of IEMOCAP. When we look at the distribution of dialogue acts and emotions, we find that statements, plain and simple statements, form the highest proportion of the dialogue acts. This is followed by questions, and then at the third position is opinions. Then when you come to the distribution of emotions, we find that neutral is of the largest proportion, followed by happy, and then anger, sadness, etc. So this data has that kind of distribution with respect to emotion and dialogue acts. Now, this is the case for modality. Are we really addressing a problem which is grounded in reality? So if you look at this utterance, Phoebe, fine, then you tell Roger, because he is really looking forward to this. This looks like a agreement or opinion, but the tone is very commanding, and the gesture is very furious. So this indicates a different emotion. The emotion is negative and maybe anger, and therefore correspondingly the response also has to be generated appropriately. So this is a case for modality because the text itself doesn't convey all these extra linguistic signals, which is important for response generation. Now I come to the techniques quickly. We exploit the 3 modalities: text, audio, and video. For the text, we use the Globe embedding. For audio, we use OpenSmile to capture various speech-related features like male frequency coefficients, maxima dispersion coefficients, voice intensity, unvoiced segmented features, speech and their statistics, and so on. And for video, we use ImageNet and pre-trained ResNet to get the image related features. So based on these three modalities and their features, we have this architecture where the input has three compartments for video, text, and audio. And the output layer, as per the problem, has a dialogue, act, classification information, and the emotion information. So emotion is 8 classes, dialogue, act is 12 classes because of these 12 categories of dialogues. The intermediate layer is called a triple attention network. It is a lot of matrix multiplication essentially, which has self-attention, intermodal attention, and intertask attention. Intertask attention is a dialogue, act, and emotion. These are the 2 tasks which are helping each other. So now we trained the system with all the data that I described, and the results were observed. And for dyadic case, which is 2-party dialogue, and that is essentially the IMO cap data, on that, the text, audio, and video, the 3 modalities combined, produced an accuracy figure of about 70%. For multi-party dialogue, the accuracy was lower, expectedly, about 50%. And when we combined both the data, multi-party and 2-party, the accuracy was about 60%. I must confess that we do not understand all numbers. We have done detailed error analysis, but we have found out again and again from our analysis that here are the supporting numbers also. When we use only one modality or use only one task, the accuracy figures are lower than multi-modality and multitask situation. So that was the main contribution from the work, that multimodality and multitask helps and can possibly reduce the requirement of data. So we did some case study also to look at the qualitative outputs, and we found that the multitask situation with text and video had much better agreement with the gold standard compared to single task. So this was the qualitative study. Now, the summary of this part of the talk is that we investigated the role of emotion and multimodality in dialogue act classification. This is very important in a practical situation like chatbot construction. We contributed the data Emoti DA, which is already being used by people wanting to do emotion, dialogue, and sentiment all together. We have given an attention-based neural network model for solving this task. And we have found that multimodality and multitasking actually boost the accuracy of the system. Now, going forward, we did a similar piece of work. There are 2 more pieces of work which I'd like to describe, but going quickly over them. This is called EmoSen. It is very similar to the previous work that I have just now described. Only thing is that this is also aware of emotion and sentiment, but the system doesn't output the emotion. The emotion and sentiment is a latent encoding, which is used to generate the response. And we find that this latent encoding helps in the quality of the generated response. Now, the motivation, of course, is that sentiment and emotion control response is very important. Another additional study in this work is that sentiment and emotion are not really independent of each other, as is intuitive. And if we capture both sentiment and emotion and use them in a multitask manner to help the either task, then the response generation is also better. Now here the input is a textual utterance along with audio and video features. Conversational history is also coming in as a context. The output is to generate the next text response. So the contributions are end-to-end framework for sentiment and emotion controlled dialogue generation. Here also we have contributed data, and we have established, we feel, a strong multimodal baseline. Now, the data was annotated based on previously available MEISD dataset. This is from 10 TV series And here the dialogues are annotated with Ekman's 6 universal emotions. We also annotate the data with positive, negative, and neutral sentiment. And there are different deep learning models which are trained on the data. So the dataset statistics, the number of dialogues is about 40,000, number of utterances is about 7.3 lakhs. An average turn per dialogue is 21. Each dialogue segment has about 21 turns. And average words in the text response is about 7. Number of emotions per dialogue is 5.5. Number of unique words is 40. The data is divided into train set, valid set, and validity set and test set. Now the architecture, there was a lot of trial and error with the architecture, and of course we made use of all traditional architectures like bidirectional LSTM, GRU, etc. But recently, I believe in NIPS 2020, there was a paper on multimodal conditional variational autoencoder. So this framework was given, and we wanted to see its application in our task, namely emotion control dialogue. And it was good to see that this new system, multimodal conditional variational autoencoder, did produce better results than other competing systems. So we had baselines like unimodal baselines, only text, audio, and video, bimodal baselines with text, audio, video, audio, video, and also trimodal baseline with text, audio, and video all together. Now, again, we looked at the numbers and had these evaluation metrics like perplexity, sentiment accuracy, emotion accuracy. Are the sentences grammatical, that is fluency, sentiment consistency, emotion consistency were evaluated by human beings also. And again, we generated many observations, generated a lot of numbers, and we saw that our proposed approach, if you see the last rows, produces highest accuracy compared to other baselines. And I don't think we had any system other than ours for this specific problem, okay, namely combining emotional and sentimental responses along with dialogue act classification. So this was a piece of work where we mainly wanted to see how latent emotion and sentiment could really aid generation of natural responses. And latent emotion and sentiment were captured by the tool of variational autoencoder, which is known to be able to capture the latent distribution on the data. Human beings also evaluated these observations, and we found that the emotion accuracy, 0, 1, is about 65% of the sentences have a correct emotion accuracy. Similar is the value for sentiment accuracy. And grammatical quality is reasonably high. About 46% of the sentences are in the category 2, which is the highest level of fluency or grammaticality. So if we look at the response generation, this is a piece of dialogue from friends. So we had all this cool stuff in the basement. No, I am paddling away. See you. Really, you got all this rustic crap for free. The gold standard response was, yeah, it is nice. And when we introduce sentiment and emotion together, then the basic model of hierarchical encoder-decoder, the response was, you don't like it, a question. And the multimodal conditional variational autoencoder with attention produces this response, I am amazed, how can you not like it? I am amazed, how can you not like it? Which is little more human and little more natural. So this we observed quite frequently. I'll show you another piece of dialogue. Oh, no, give me some specifics. I love the specifics. The specifics were the best part. Hey, what about the scene with the kangaroo? Did you like that part? So these were 4 sentences coming in a context. The basic model, which did not make use of any emotion or sentiment, the response was, sure, I did like it. And then we introduced attention to a number of emotions like disgust, fear, and positive and negative sentiments. and you can see the final output. That movie scares the hell out of me, especially the end part. Okay, and the first statement was, sure, I did like it. So the emotion has changed in the output, and also seems to be closer to what a human response would have been in that situation. So this was observed in the context many times by us. Now,
So,
when we did,
can I ask
yeah,
a question
please,
here?
please,
Yeah.
please.
So, so even, I don't see an evaluation of the relevance. So suppose
Okay.
this example that you mentioned, that movie scares the hell out of me. From the
Right.
context, there is nothing to tell us that we are discussing a movie. So how is the last response, even though it exhibits the emotions and sentiments that one is after, relevant
Right.
to that conversation?
Yeah. So you're saying, is the content consistent with the context, right? So,
That's right. Yeah.
right. So that evaluation was done, and that was, the human beings' evaluation was grammaticality, sentiment, and emotion, and I think I do not show it here, but the previous piece of work which I discussed, there you possibly had seen CA, the content accuracy. Okay, and that content accuracy, I don't know how I missed it, that table. That content accuracy is also calculated. Okay, where the human beings sit down and see if the response is really consistent with the context.
Okay.
I seem to have missed this important part. Yeah, thank you. So when we did error analysis, we found that proper nouns are sometimes missed, and there is repetition. I mean, she probably talks a lot and eats a lot. The predicted response was, she talks lot. Then there was emotion and sentiment mismatch. Anger was coming with positive sentiment. Joy was coming with negative sentiment, and there were class confusion. Especially the negative emotions are very confusion prone. Anger, disgust, sadness, all of them are negative emotions, and the system often confuses the emotion. Now, there were other pieces of work in similar line, and also a lot of work which came before for dialogue sentiment analysis and dialogue emotion analysis. The final piece of work is on inducing courteous behavior in customer care response. So here, we are interested in making the output of a chatbot more polite. So we'd like to give it a kind of politeness coating. The politeness remark or respectful act is an act of courteousness, and our domain was customer care on Twitter. Input was generic chatbot reply, and output was a polite reply, which is emotionally aware, uses courteous phrases and emoticons to display appreciation, empathy, apology, and assurance. So here are some examples. You will just came to my house like last week, and I'm having problems with my internet again. System, what is happening with your internet? So we would like the system's output to be more polite. Oh no, that is not good. I can help. What is happening with your internet? User, I think there is an outage. System, there may be maintenance work in your area. Please direct message your info. System, there may be maintenance work in your area. Please direct message your info. Thanks for using our services. So we are interested in addressing this problem. Again, very novel. I don't think we saw any prior work on politeness embellishment on chatbot output. So again, the challenges were unavailability of data, annotation of the data. Yeah, sorry.
Can I just ask one more question?
Yeah, please.
Most of the time, people get annoyed by ineffective politeness. So very often customer service agents, they waste too much time in repeating these generic sentences like thank you for your using our services. And
Right.
I would in fact much rather go for effective politeness. So these are, to me, these are like stop sentences. Thanks for using our services. There is no relevance. It's a meaningless act of politeness. So is there
Yeah.
some kind of intermingling of meaning with politeness?
I think Sunita, it also is personality dependent. These phrases like thanks for using our services, these are like maybe lubricants, okay? And too much of these will be an irritant, definitely, no doubt about this. But maybe your question is there a good balance of content and this kind of politeness phrases? Okay, is
Yes,
that
yeah.
right?
I mean, that's my technical question. That
Yeah.
this politeness,
Ah.
if it comes out just by sort of rhythmically introducing these generic sentences, then it's not technically very hard. Whereas if you could intertwine with the content the politeness, then it's sort of it's non-trivial. That task,
Yeah.
the output is also non-trivial.
Yeah, a very, very nice point. And actually, this point is coming up as we go ahead. So you're also pointing to diversity of politeness phrase generation. It should not be always thanks for using your services. Okay, it should be consistent with the content and the context. So the politeness expression should be conditioned on the content. Not only that, it should also depend on the person involved. So the next piece of work, which I am not presenting today, is politeness generation consistent with the age and gender. Okay.
Professor Bhattacharyya?
Yeah.
Yeah, this is Rajesh here. One more thing that's important in this context is the country where you are from, or the country in which this conversation is happening.
Yes.
And if you're in Japan versus if you're in US or UK, it's a totally different frame of reference when it comes to politeness.
Correct. So our latest piece of work really takes into account these signals also, the gender, age, and also the cultural background, I think. Yeah. So Sunita, we're coming to that point. So where the diversity of the politeness phrase is ensured by a reinforcement learning component. Okay, I'm just coming to that. Okay, so these are the challenges, and I think the contributions are the novelty of the problem, the data set, the benchmark model that we have created, and it is also a contribution to natural language generation because the output needs to be refined based on the situation. So the data was Twitter data from Kaggle, and we looked upon the problem as a machine translation problem. The source side is just content, and target side is content embellished with politeness phrases. So this data was processed by removing the politeness phrases and keeping only the content part of the sentences. So we got a kind of parallel corpora, and this gives the dataset statistics of about 2 lakh conversation. Total utterances were 4.5 lakhs. Training conversations were 1.4 lakhs. Validation to 20,000, and a test was done on 40,000 sentences. So the generic output input is how can we help, and help has arrived. We are sorry to see that you are having trouble. How can we help? So the behavior here is apology. So these kind of courteous responses were categorized into apology, greeting, assurance, empathy, appreciation, and so on. Now again, the deep neural network, which essentially is a lot of matrix multiplication. So we used a hierarchical sequence-to-sequence transformer. The dialogue is a sequence of turns, and each turn is a sequence of words. So in the baseline system was a sequence-to-sequence encoder, just like in machine translation. So when we had that system, we found that the politeness phrases were very repetitive and boring. They were coming again and again. And as Sunita said, this is not a very complex problem because it is like a machine translation situation where these phrases would be inserted into the output automatically depending on the context and the probability values. So what we did was we changed the loss function and introduced a reinforcement learning component into the loss function. So there is this maximum likelihood component and the reinforcement learning component. I don't think we have time to detail out all the mathematics and all the considerations. So the reinforcement learning, the reward function came from the blue score value. Okay? So when the system generated a response, the politeness phrase, if it was repetitive and monotonous and boring, then the reward fell. And that reward function was computed from what is called the blue score, that is the n-gram match of the output along with the reference generation. So this component, through this kind of policy, that is reward based on the actions, actually ensured more diversity in the politeness expression generation. And then we again did a lot of evaluation on the data and had both automatic evaluation and human evaluation. The blue score captured the fluency and adequacy, that means the content preservation, as well as the grammaticality of the sentences. Rouge score also did the same thing, perplexity, and then emotional accuracy. All these were automatically evaluated based on the levels. But more important was human evaluation, who did CA, that is the response accurate. COA is courtesy appropriateness, and F is fluency, which is the grammaticality and well-formedness of the sentence. So this kind of content preservation was always studied in all the three pieces of work, which is actually the point of relevance of the response with respect to the context. And we could see that our proposed model had better values than all the proposed baseline. Now, some of the qualitative study of the output is also shown here. For example, if you look at the last line, fill this form, the baseline model produced, please fill this form. Model 2 said, we are here to help, fill this form, and I'll contact you at the earliest. Model 3 said, apologies for the hassle. Please fill this form and we'll contact you. Thank you for reaching out to us. We'll follow up with the store. And our model produced, I'm sorry for the hassle. Please fill this form and I'll contact you at the earliest. So the models are pretty close to each other. And we could see that we could achieve some kind of distance from the baseline response in terms of politeness score. So I'd like to now summarize the talk with a few summary observations, draw some conclusions, and point to some future directions. So we initially covered NLP and the complexity of ambiguity in NLP, the relationship of NLP and ML. ML provides the classifiers to do disambiguation, sentiment and emotion analysis background in terms of this 5-tuple definition, multitask, multimodal dialogue generation, which was the first piece of work. Emotion and dialogue turn should be done together. Also, speech and video signals should be taken into account. Then multimodal dialogue generation, where the emotion and sentiment are latent. Okay? They are not visible to the observer. And then politeness transformation on the chatbot output. So the conclusions are making computers human, I think, is becoming a reality slowly. Many problems which you could not even imagine were solvable are actually making inroads into some kind of solution. Understanding and producing sentiment and emotion is a highly interesting and practical problem. There are many organizations, including insurance companies, airlines, who approach AI researchers for working on emotion-aware chatbots. Banks also do that. Deep learning with data is the key methodology. But the challenge of deep learning, all of us know, they are very data hungry, and explainability is indeed a problem. Now, research directions are, of course, deep learning with less amount of data. Cross-domain and cross-lingual assistance is becoming important, again, because of the paucity of data. And one interesting thing, I think, is designing the right loss function for these problems. Then many tasks, I think, depend on an appropriate loss functions. So everything I said is linked from my homepage, and we have contributed these resources from the lab homepages at both IIT Patna and IIT Bombay. And thank you very much for your attention.
Okay, thanks a lot, Pushpak, for the great talk. I think we have some time for a few quick questions, if there are any. Please unmute yourself and ask. Okay, if there are no further questions, then we'll thank Pushpak once again.
I have one question.
Sure.
Yeah.
Go
A
ahead.
quick one, yeah. Rajesh here. Professor Bhattacharya, this was a very interesting talk. The
Thank
one
you.
thing that I'm not from this field in the sense that from programming, excuse me. So I'm not able to wrap my head around how do you create these responses which are automatic? I mean, isn't there a human being involved in creating these responses as a first order reference?
You mean creating the data, right?
No. If somebody asks some question, then you're creating a response, right? Automatically through your magic.
Yeah. Right. So your question is, how is the response getting generated?
Yes.
Okay.
Yes.
So the question is, how are the words generated and how are they placed with respect to each other, obeying the syntactic rules?
Correct.
Right.
Yes.
Maybe that is your question. So how do you generate the word and how do you place the words in the correct order? So this is the well-known decoding problem. So I think the main contribution to this has come from machine translation, where you have encoding and decoding, in the sense that the input sentence is converted into a kind of vector. All the words are pre-trained vectors, and their combination is also a vector which comes out from the encoder. Now, this activates neurons in the outermost layer. And neurons or groups of neurons are responsible for particular words or phrases in the language. So there is a large number of neurons in the output layer. So when these neurons get activated, they point to a particular word being the winner word at that position. Okay, and the syntax or the order of the words is also similarly arranged because of the decoding mechanism. I mean, that would be a top level simple answer.
I think, I understand that. What I was looking for is, let me give you an example, right? For example, I have Alexa, Siri, and Google at my home, right? And when I ask the same question to all three of these, they give a very different answer. So it tells me that somebody is programming them to say different things. Is that true, or is it completely based on the algorithm?
Well, I don't know, but it is possible that, on the same data and two different models trained on the same data with different hyperparameters would produce very different responses. But it is also true that many of these companies actually, give human-generated responses. And especially if some question has been answered before, I don't think they again launch a computation. They just retrieve it from the database.
Oh, I see. Okay.
Yeah.
Thank you.
Okay. Right.
Small clarification, Nikhil, is it okay?
Sure. Yeah, sure.
So, Professor Pushpak, just curious, some details about this last topic called reinforcement learning. Is there any particular algorithm that was being used there within this RL, or?
Yeah. So.
Is it like an actor algorithm or something like that, or?
Okay. So, if I recall correctly, I think it is for dynamic queue learning or some such thing.
Okay. Speedy queue learning or something like that. Okay. Maybe your papers will have some details. Maybe I can look it up there.
Surely.
Thank you. Yeah.
Okay. I guess that brings us to the end of the session. Thank you again to Pushpak, and we'll see you all next time.
Okay.
Right.
Thanks very much.
Bye.
Thank you.